Welcome back. It's time for section 7.10. All right, so section 7.10 is a really cool section that talks about something that maybe you haven't ever heard before, but it is kinetic isotope effects in elimination, specifically E1 and E2. And kinetic isotope effects are really unique in organic chemistry and pretty cool. For this reason, how many isotopes of hydrogen do you think there are? We're used to protons, right? Those are just one proton, and then we know that the atom of hydrogen has one proton and one electron. But what if I told you there were 3 isotopes of hydrogen? There's protium that has 1 proton, 0 neutrons, and 1 electron. There's deuterium that has 1 proton, 1 neutron, and 1 electron. And then there's also tritium that has 1 proton, 2 neutrons, and 1 electron. And what's really cool about these 3 isotopes is that the weight increases by 100% each time. This one weighs 1 atomic mass unit, this one weighs 2, and this one weighs 3. And so that means that some reactions are going to be much different based on their size, because carbon deuterium bonds are actually a lot stronger than carbon hydrogen bonds. And the same goes for tritium because they're much larger and can have better overlap. So let's take a look at how this affects both E2 and E1 reactions. So to perform a kinetic isotope effect experiment, it's actually fairly straightforward. What you do is you run a reaction using a molecule that has all hydrogens. So in this case, we want a base to deprotonate one of these hydrogens on the beta carbon of an alkyl bromide so that we can make the alkene and kick off that bromide in an E2 fashion. So when we do this, we'll generate a rate law that is based on the rate constant for molecules containing all hydrogen times the concentration of our alkyl bromide in our base. We compare this rate constant with the rate constant obtained by using a deuterated version. We say deuterated because deuteriums have replaced hydrogens in some places in the molecule, and especially for this reaction, they replace the 2 hydrogens that might be deprotonated. So we run this reaction, we get our deuterated alkene, and our base, this should be D and not H here. Sorry about that. I'll just mark that. There we are. Okay. Base deuterium, and we kick out the bromide. And this time, the rate law is going to be equal to the deuterium rate constant times the deuterated alkyl bromide times the base. And as long as we keep the concentrations of these 2 and these 2 the same in both reactions, then we can directly compare the 2 rate laws. And what's really crazy about this is that KH, the rate law for the fully hydrogenated version, does not equal KD. There's a difference, and it's a huge difference. In fact, KH is almost 7 times bigger than KD. And this is based purely on the fact that the CD bond, this one, is much stronger, and so it's a lot harder for a base to deprotonate because of the bond strength. And this brings us to talking about isotope effects in general, now that you've seen how one of these reaction studies can go, because the most important part about isotope effects is that the hydrogen version does not equal the deuterium version. That is, the rate constants are not equal. So we can actually find out a lot of really cool mechanistic information from this, because if KH over KD, so the ratio is between 3 and 8, we call that a primary isotope effect. And a primary isotope effect indicates that the CH bond being broken, which was in this case the CH bond during deprotonation from the base, we say that that step is the slow step in this reaction. Now with E2, reactions, that's fairly convenient because there's only one step. So that step must be the slow step. But we can use this throughout many different types of reaction investigations to find out what the slow step is. Now, Kh over Kd can also be much closer in value. If Kh over Kd is almost the same between 1 and 2, that means that's what's called a secondary isotope effect. And that lets us know that there is still some CH bond that is being broken during the reaction, but it's not the slow step. And so the variation in deuterated versions versus hydrogen-containing versions is much smaller. Now we've seen what happens in an E2 reaction where the CH bond was broken in the slow step, but what if we talk about an E1 reaction? Because in an E1 reaction, we already know that the slow step is the leaving group leaving and not the CH bond being broken. So in this case, we would expect for there to be a secondary isotope effect because we already know what the slow step is. So if we do our experiment here using a completely hydrogenated version with all hydrogens, you can see that the rate is again equal to the hydrogen containing rate constant times the concentration of the original alkyl halide. And the deuterated version here, we run the exact same reaction, and the rate law is then equal to the new rate constant, the deuterated rate constant, times the deuterated molecule's concentration. And as we expect, Kh over Kd is almost 1. There's basically no enhancement in having a deuterated version over a hydrogen-containing version, which tells us that the two rates are basically the same because the slow step is in the leaving group step, the very first step in E1. So the take-home message here is that kinetic isotope effects can be a very good way to study reaction mechanisms and can let us know what the slow step of a reaction is. And using that, we found out that E2 reactions have a CH bond being broken in the slow step, as we know, and E1 reactions don't. And this was section 7.10.